Hello, so today we are going to take a look at this problem called number of subarrays with add sum. And so the problem says we get an array of integers and we want to find the number of subarrays that have an add sum. So how many subarrays in the array have an add sum? When we sum them up, we get an add value. And we want to just return the sum modulo this number just because it may get too big and we don't want to get into issues with that. So if we take as an example this array 3, 5, 7, all the subarrays in this array are 3, 3, 5, 3, 5, 7, 5, and 5, 7, and 7. And so if we take all these subarrays, their sum is these values here. And so if we look at these values, what are the add values? We have 3, 15, 5, and 7. And so overall we have 4 add sums, and so we should return 4. For this here, the result should be, 0 here, because we have only even numbers, and so there's the subarrays here are all even, and so we have 0 add some subarrays, and so we should return 0. So this is the problem. Now let's see how we can solve it. Okay, so let's see how we can solve this problem. So the main idea that we will use here is dynamic programming, but let's just sketch out what we need to do. So the examples, one of the examples we had is an array like this where we had 3, 5, 7, right? Now for a dynamic programming solution, what do we need to do? Right? We need to specify a couple of things. So the first thing we need to specify, well, what is our goal? But just before that, I want to go on a little bit of a tangent here to just lay the foundation for this solution here. So one thing we know that here is that a couple of things. If we add an add value, let's say 1, and an even value, then we will get always an add value, right? And then the same if you reverse the order, like an even plus add, that still will give you also an add value. But when you add 2 even values, you get an even value. And then when we add 2 add values, we get an even value, right? Because let's say, for example, you add 3 plus 3, that will give you 6, still even. So that's one of the rules that we will rely on, right? Whenever you add 2 values that have different parity, you get add. And when you add 2 values that have the same parity, you get even, right? So that means that we can kind of simplify the problem a little bit and do a pre-processing step and just convert every add value to 1 and every even value to 0, because at the end, the sum would be the same, like the parity of the sum would be the same, right? If you had 3 plus 5, right? So this is add, that would be 1. This is add, that would be 1. So you add this up, this is even. Well, that's already true because here 8, this is even, right? So in terms of like parity, even or add, we could just always simplify any odd number to 1 and any even number to 0. So we can do this pre-processing step before doing anything else. And then from there, we reduce the problem to a simpler one, right? So here, what this would mean is that our pre-processing step is just convert add to 1 and even to 0, right? So what this would mean here for 3, 5, 7 is that this would become, well, 3 is add, so 1, 5 is add, so 1, and 7 is add, so 1, right? If we had, let's pick another example. Let's say if we had 4, maybe let's say 5, 8, 7, 12, right? So this one would be 0, 1, 0, 1, 0, right? So this simplifies the problem into a simpler problem. So let's just say simplification here now. Instead of looking for the add sums, subarrays with add sum, now we are looking just for subarrays with sum 1, with sum equal to 1, which is a lot easier to find, right? Because while we are summing, if we get 1 plus 1, that would be 2. We will also convert that to 0 because it's even. If we get, let's say 1 plus 1, if we get like 2 plus 1, we won't get 2 plus 1 because every time we add 2, we will convert to 1 or 0 depending on the parity. And so if we get 1 plus 0, that's also 1, right? So we will always keep being 0 or 1. Those are the only two sums that we will have, right? And so now the problem is just finding the subarrays with sum 1. And so how can we solve this one? That's where we are going to use DP. So with our DP solution, we need to find a couple of things. The first one is the goal, right? And then after that, we will need to find like the state that we are going to do DP in. And then after that, we need the base case. And then after that, we will need recurrence relation. So these are the different things that we need for a dynamic programming solution. And then sometimes, most of the time, the order of iteration is just from 0 to the length of the array, but sometimes it can be different. And sometimes we need to change the order of iteration from the usual 0 to n to the length of the array. And so here we need the order of iteration. Maybe let me just put this all the way down so I can have some space here. And after that, we could just return the result, right? So let's fill in these different things that we need. So what is the goal? So the goal that we are looking for here is the number of subarrays in, of course, the transformed array. In the transformed array that sum to 1. So this is what we are looking for, right? So to do that, basically what will happen is that if we have sum of 1 and then we had a previous subarray that have sum of 0, then adding on 1 here makes this entire thing have sum of 1, right? So to calculate the sum of 1, we need to know what subarrays had sum of zeros, right? So we kind of need two states here. We need the DP state for the sums that are 1, and then we need for 0 because that's where for I plus 1 we will use DP of 0 for I we will use DP of 0 for I plus 1 if we choose the order of iteration to be decreasing, right? So this would be 0 here. Don't worry, this will be more clear in a second. And so here for at position I, and this at position I, what would this be? So here this would be the number of subarrays starting. I'm going to choose starting at I here. We could choose, of course, ending at I and do the calculations differently, but for my use case here, I'm going to choose starting at I. And of course, ending at the end of the array, right? This is just explicit here. Let me just ending at end of array, just to make sure we know what we are doing here. And then here, this is the number of subarrays. I didn't finish this sentence here. This here, that's sum to 1, of course. Those that sum to 1. This is DP of subarrays starting at I that sum to 0. So these are the two states that we'll need to do. And the goal function here that will return at the end would be DP, would be just the sum of all DP of 1, right? Because DP of 1 represents all the number of subarrays that sum to 1, right? So if we add all of them up, we get all the subarrays that sum to 1 in this array. And that is the equivalent of all the subarrays that have an odd sum, because if they have sum 1, that means that's an odd sum, right? And that's exactly what we are looking for. So now what is our base case? So in my use case here, since I said starting at I, that means that at I position, I want to have already computed all the way until n, right? Because I want starting at I, so I need to have all of this starting at I plus 1 to be able to compute, just add this one and compute it, right? If I had done ending at I, then I would have needed all of this starting from 0, right? But what I'm doing is just going this way instead. That's why I'm choosing starting at I. So the first thing I will need to use here is the n-1 position. If I had ending at I, then my base case would have probably been starting at 0, right? And so this is usually kind of how the base case relates to the state here. And so what I need here is to find dp of n-1 for both dp1 and dp0, right? So let's see. So here that would mean that dp of 1 at n-1, what would that be equal to, right? So this one here would be equal to 1. If the element at this position is 1, then that's 1, because the element, that means the number of subarrays starting at n-1 that sum to 1 is equal to 1, right? So this is only if this is equal to 1. And dp of 0 is at n-1 is equal to 1 only if array at position n-1 is equal to 0, right? Because if you have 0 here, then the number of subarrays starting at I that sum to 0 is equal to 1. But if this is 1, then that's 0. So those are the two conditions. So maybe let me just rewrite these in a nicer way here, so that's super clear. So if the array at last position is 1, then that means that the number of subarrays starting at n-1 that have sum 1 equal to 1. If it's 0, then it stays as 0, so I'm not going to touch it, because I'm assuming here that we will initialize dp of 1 to all 0 elements, n0 elements, and dp of 0, it would be all 0 elements, and it will contain n elements, right? So if array at position n-1 is equal to 0, then we'll just leave the initialization value, which is 0. And for dp of 0 here at position n-1, else here, that means the element at position n-1 is 0. So that means the number of subarrays starting at n-1 that sum to 0 is 1, right? And so this is our base case. Now, how can we do our recurrence relations? Now, our recurrence relations, in the same way that the base case is dependent on the value at n-1 position, they will depend on the value at I. So if that's equal to 1, then we would have a set of things, and if it's equal to 0, we would have a set of other things, right? So let's examine this, right? So let's examine the first case where it's equal to 1. So the first case when it's equal to 1 here, so we have 1, and then we have a bunch of other elements. And then here, this is the rest of the array that we haven't examined yet. Maybe let me just put the portion that we haven't examined like this. Okay, so this is position I, and this is I plus 1, and we are going this way. So at position I would have already the state at position I plus 1, right? So we will need to write dp of 1 at I as a function of either dp of 0 at I plus 1, or dp of 1 at position I plus 1, or both, right? We don't know. So, and the same thing for dp of 0, it would need to be written at depending on these two, because those are the only two states that we have here. So of course you could also say we could use I plus 2, I plus 3 all the way until n, but using these is probably enough, right? So let's see how can we write dp of 1. So if we are at this one here, right, and then we have a bunch of values, then what we can say is that dp of 1 at position I, this one here, depends on dp of 0 at position I plus 1. Why is that? It goes back to the property that we said here. that even and odd will give you odd, and then odd and even will give you even. So because if you have sum 0 and you add 1, you will end up with the sum of 1. But if you have sum of 1 and then add 1, you would end up with sum of 0. So dp of 1 at position I will only depend on dp of 0 at position I plus 1, because that's the only thing that will give us a sum of 1. And now we have all the subarrays here that sum to 0. You could add to each one of them, add 1, and get a new subarray that sums to 1, right? And so we know that dp of 1 at position I is definitely dp of 0, but maybe it's plus at position I plus 1, because each of them will add 1 and it becomes of sum 1, and so we could count it. But this one alone also is a subarray and it has sum of 1, so we need to add that one here. And of course, whenever we add 1, we need to do the mod. So that's for dp of 1. So let's write this down here then. So we know that dp of 1 at position I is going to be equal to 1 plus dp of 0 at position I plus 1, and then we will need to do mod here, right? Now what about dp of 0? So dp of 0 means that we have, so if we have 1 here, right, and then we have a bunch of other values, so these are, so dp of 0 here would be, so if we had arrays that have sum 1 and you add 1, they would have sum 0, right? Because 1 plus 1 that gives you 2, it's a 0, because it's odd with odd that gives us even, right? So that means that dp 0, to get a subarray that has sum 0, we will need to use dp of 1 at I plus 1, right? So this means that because every subarray that has sum 1, if we add it with this one, it will have sum 0, because we do always mod with 2. And so we could just count all the dp of 1 at position I plus 1. And this subarray alone has sum 1, so we don't count it toward the subarrays that have sum 0. And so that would mean that this is the final formula for dp of 0. And so let's write this down here. So this would mean that dp of 0 at position I is equal to dp of 1 at position I plus 1. Okay, so now that we have this, let's check the second use case, which is when we have 0 instead. So if we have 0 like this at position I, let's say we have 0, that's where array at position I is equal to 0, and then we have some other elements here, and then we have the rest of the array here, right? So how can we write dp of 1 at position I at this point? So at this point, dp of 1 at position I, it will depend on, because this is 0, right? Because this is 0, we would have 0 like this. Maybe let me pick another color. So we'd have 0 like this, and then we would have a bunch of other arrays. So if these arrays were of sum 0, then if you add this 0, it will still be 0, so they will still be sum 0, so that doesn't count toward the subarrays of sum 1. But if they had sum 1, then each of them we could pair it with this 0, and we will get a subarray of sum 1, right? Right? Of course, starting at I plus 1. So we don't have 1 really that starts here. They all start at I plus 1. And so dp of 1i depends on the subarrays that start at I plus 1 that have sum 1, because if we add 0, they will still have sum 1. So it will depend on dp of 1 at I plus 1. And the subarray of value 0 itself doesn't count because it has sum 0, so we don't count it. So that would mean that dp of 1 here at position I is going to be equal to dp of 1 at position I plus 1, right? Now what about dp of 0, right? So for dp of 0 here, now when we have 0 and we have a bunch of arrays, a bunch of subarrays here that are starting at I plus 1, so maybe this one, and then maybe this one, that sum to 0. So if these sum to 0 and then we add 0, we still have subarrays of sum 0, but if they sum to 1, then we would have subarrays that sum to 1, so we can't count those. So we need to use only those that sum to 0. So it depends only on, dp of 0 at position I plus 1. But again here, this element 0 alone by itself is a subarray of sum 1. Sorry, subarray of sum 0. And so we need to count it. And so that would mean that our dp of 0 here is equal to 1 plus dp of 0 at position I plus 1. And we do mod, right? So that means that we could just write this again here, and that finishes up our transitions or our recurrence relations. So here that would mean that dp of 0 at position I is equal to 1 plus dp of 0 at position I plus 1, and we need to pick the mod. Okay, so now that we are done with the recurrence relation, what about the order of iteration? So since we wrote our recurrence relation here for I depends on I plus 1, so it depends on from I plus 1 to n. So that would mean that we need to be going this way. We need the order of iteration to be going this way. And that's what we used also the base case. The base case started at n minus 1. So that would mean that we are going to the left like this, right? So what this means is that our order of iteration will need to be decreasing. So, and since we already handled the base case, n minus 1, that means we can start from n minus 2 and go down to 0. So this would be our I, and we will be decrementing our I. So this would be, well, what this would mean is that our for loop would be in range decreasing from n minus 2, decreasing by 1 until it reaches 0. This is just Python notation. We could also do it with Python notation using n minus 2 and then reverse. Basically from 0 to n minus 2, to get to n minus 2, we need to do n minus 1, and then reverse so that we can start from n minus 2, right? Okay, so now with all of this, we have everything we need to do our dynamic programming solution. We know how can we, once we have dp of 1 and dp of 0, specifically dp of 1, we just can take the sum and get the goal, what we are looking for, which is the number of subarrays that sum to 1, which can be mapped back to the subarrays with add sum. That's just because we simplified the problem down to that. And then we know how to determine our state, we know how to do the base cases, we know the recurrence relation, and we know how our for loop would be written. So we could just start writing this down. So let's do it. So then number of subarrays with add sum, we'll get an array here, right? And so the first thing we need to do is, of course, just get some variables in place. So we need the length of the array, and we need to define the mod value, which is 10 to the power of 9 plus 7. And then what we need here is do the simplification here, or the conversion of the array from this to only 0 and 1 values, because that's what we are interested in here. So to do that, we'll just go through the array, the indices of the array here. and we'll say that for each one of them we are going to pick it modulo 2, and from there we can define our DP arrays. So this would be, we would initialize it for 0 values, and we will have n slots, right? Because that's what we need to fill up here. And then we will define the same in the same way DP of 0, which will contain the number of subarrays starting at each position I that sum to 0, and a similar thing for DP of 1, except it's sum of 1. And from there we need the base case, right? So we need to handle the base case here. So base case, and our base case would be that if the array at position n-1, which in Python we can write as -1, is equal to 1, then we will just say that we have one subarray, right, that has sum 1, that starts at n-1. And so we could just say n-1 again can be just written as -1, but let me just maybe make this more clear by doing n-1. So this would be n-1, and this here n-1, this is equal to 1. And for if the element at position n-1 is 0, we just have DP of 0 at n-1 is equal to 1. And now that we are done with the base case, we need to do the recurrence, right? And so to do that, we will use the order of iteration that we determined here, which is from n-2 down. And so in Python, we could do that with in range of n-1, so that we can get n-2, and then reverse the whole thing using this, so that we can start from n-2 and keep going down. And now we'll just copy over our recurrence relation that we've done here, which says that if the element at position I is equal to 1, then our DP of 1 at position I would be equal to 1 plus DP of 0 at position I plus 1. So we already explained that. Modulo mod here. And DP of 0 at position I would be equal to DP of 1 at position I plus 1. And then with the else here, we said that DP of 1 at position I is equal to DP of 1 at position I plus 1, right? Nothing changes. And then DP of 0 at position I is going to be equal to DP 1 plus DP of 0 at position I plus 1. So it would be 1 plus DP of 0 at position I plus 1, and we need to take the whole thing mod. So this is just the exact same recurrence relation that we written earlier. And now we can find the solution once this iteration is done. So now here, get the solution, which is pretty much what we defined here, that it's the sum of all DP of 1s, because the sum of all the number of all subarrays that have an odd sum, that's the number of all subarrays that have sum 1. So that's just the sum of all values of DP of 1. And so to do that, we could just take a variable here, call it maybe res, and then go through DP of 1. And then for res, just add up the value here d, but for this d we need to take mod again. So always take mod so that we don't go over the limit, and here return res. And that's pretty much it. That's pretty much the solution here. So to reiterate again, simplify so that we can have only 0 and 1 values. Start our DP by defining the base cases, the recurrence relations, and then at the end do our solution calculation. Yeah, so that's pretty much it. Let's run this on some examples and make sure it passes test cases. Okay, so I wrote down the solution here, the same solution we just went over, simplifying the array, and then doing the DP solution here, to find the number of subarrays that have sum 1, and then taking the sum of those that have sum value of 1, which gives us the number of subarrays that have at sum, right? And here are some test cases just to make sure the solution works. So I run it, all test cases pass. Of course, this is not exhaustive, but this should work fine with any test case. But if we just talk a little bit about the time complexity here, so if we look here, we have this for loop here, oven, and then this for loop, which is oven. So only 2 loops, and this third loop, which is also oven, since dp of 1 has size of n. So at most we'll do O of 3 n's. So this would be overall is oven time. Now in terms of space, we have these 2 extra arrays that have each size of n, right? So this would mean that we have O of 2n, and so overall is O of n space. Yeah, so O of n time, O of n space. Okay, so that's it for this problem. Thanks for watching, and see you on the next one. Bye.